Dear students, Assalamu alaikum. Today I am again with you with another class for class 12th, and we are dealing with current electricity, and today's topic is Kirchhoff's laws or Kirchhoff's rules. As you know that in more complicated circuits such as radio, receiver or television set, etc., which cannot be reduced to simple series and parallel arrangements, the equivalent resistance of the circuit or the current or the potential difference across any resistance in the circuit can be determined by using Kirchhoff's laws. These laws were introduced by Kirchhoff in 1942. He gave two laws or two rules. The first law is known as Kirchhoff's junction law, and the second law is known as Kirchhoff's loop law or loop rule. Now, what is junction law? It states that at any junction, the sum of the currents entering the junction must be equal to the sum of the currents leaving the junction. This law is based on the conservation of charge. That is, the charges are not accumulated at the junction. Let us take an example. Consider a junction O in the electric circuit at which currents I1 and I5 are entering the junction and currents I2, I3 and I4 are leaving the junction as shown in fig. Now look at the fig. You can see that there are two currents which are entering the junction O. Junction means where the wires coming from different directions meet. So this point O is the junction. Here these three wires join together. So this is called a junction. And we see that at this junction, two currents, I1 and I5 are entering the junction, and I2, I3 and I4 are leaving the junction. So Kirchhoff's first law states that the sum of the currents, so sum of the currents entering the junction, that is I1 plus I5. I1 plus I5 must be equal to the sum of the currents leaving the junction. That is I2 plus I3 plus I4. I1 plus I5, these two currents are entering the junction, and I2, I3 and I4, sum of these three currents which are leaving the junction must be equal. Sum of currents entering the junction must be equal to sum of the currents leaving the junction. Or in other words, we can say that the algebraic sum of the currents meeting at the junction must be 0. This is the other statement of Kirchhoff's junction rule. That is, the algebraic sum of the currents at the junction must be 0. That, as you can see from here, this is the algebraic sum. We can write this I1 minus I2 minus I3 minus I4 plus I5 is equal to 0. Then we take I2, I3, I4 towards LHS. So you can write this I1 plus minus I2 plus minus I3 plus minus I4 plus I5 is equal to 0. So this is the algebraic sum. The algebraic sum of the currents meeting at a junction in a closed circuit is 0. So this is Kirchhoff's first law. This is based on conservation of charge. Conservation of charge. That is, charge cannot accumulate at the junction. Charge must be conserved. The amount of charge entering the junction must be equal to the amount of charge leaving the junction. So this law is based on conservation of charge. Now there is second rule or second law, that is Kirchhoff's second law, that is known as loop law, or it is known as loop rule also. It states that in any closed loop, the algebraic sum of the EMF is equal to the algebraic sum of the products of the resistances and respective currents flowing through the closed loop. This law is based on conservation of energy or electric field. The first law is based on conservation of charge. The second law is based on conservation of energy or conservation of electric field. Now let us take the example which can make it clear to you people. Consider a closed electric circuit containing two cells of EMFs E1 and E2 and three resistors or resistances R1, R2 and R3 as shown in the figure. Now you can see that there are three loops, two smaller loops and one bigger loop. As you can see here, it is the loop A. If the direction of the path taken to go around the loop is the same as the direction in which current I moves in the source, then E and IR are taken to be positive. What does that mean? That is, if we follow the current, if we follow the current, we then these are taken as positive. E, EMF and product of I and R are taken as positive, and vice versa. Now applying Kirchhoff's second law to the loop A, B, E, F, A. A, B, E, F, A. That is the upper loop. A, B, E, F, A. A, B, E, F, A. This is the upper loop. We see that E1, there the source of EMF is E1 in this loop. That is E1 is equal to I1 R1 plus I3 R3. So there we have only one, in this loop we have only one source of EMF, that is E1. So E1 sum of EMFs will be equal to E1. So E1 must be equal to the sum of the products of currents and resistance, that is I1 R1 plus I3 R3. Again apply Kirchhoff's second law to the loop CBEDC, that is the lower loop in the field. CBED, we get E2. There we have only one source of EMF, we have only one cell, that is E1 in this loop. So E2 will be equal to I3R3 plus I2R2. Here in this case we are following the current. We move behind the current. If we in the opposite direction, in loop first, if we move in the opposite direction, then it will be minus E1 is equal to minus I1 R1 minus I3 R3. Similarly, in the second case, it will be minus E2. If we go in the opposite direction of current, it will be minus E2 equal to minus I3 R3 minus I2 R2. So that will be the same case, because we can take minus common, the result will be same. So now apply Kirchhoff's second law to the loop, that is the bigger loop. Combining the two loops A, B, C, D, E, F, A, and moving along A, B, C, D, E, F, A, we get minus E2. Here we go against the current, plus E1. Here we go in the direction of the current, will be equal to minus I2 R2, because here we go again in the opposite direction of current, and plus I1 R1. Here we follow the current, we go behind the current. E2 and I2 R2 is negative because we move in opposite direction of I2. This implies E1 minus E2 is equal to I1 R1 minus I2 R2. If we move along A, F, E, D, C, B, A, then we get minus E1 plus E2 is equal to minus I1 R1 plus I2 R2. Here E1 and I1 R1 is negative because we move in opposite direction of I1. This implies minus E1 minus E2 is equal to minus I1 R1 minus I2 R2, and this minus will cancel. We will get E1 minus E2 is equal to I1 R1 minus I2 R2. So this implies that if we go in opposite direction to the current, or if we follow the current, in both the cases the result will be same. In both the cases, the result will be same. So these were two laws of Kirchhoff. Now we will discuss the application of his laws. The first application of this Kirchhoff's law is Wheatstone bridge. Wheatstone bridge. Wheatstone bridge is a circuit. Wheatstone bridge is a circuit. It is an arrangement of four resistances. Here we have four resistances, three of them are known, and the fourth can be determined in terms of the three known resistances. If we know the three resistances, then we can determine the third one. It consists of three resistances, three known resistances P, Q, and S. These are the three resistors which we know. We know their magnitudes, and the fourth unknown resistance are which we don't know. We don't know the magnitude of the fourth resistance. A source of EMF is connected between point A and C, as you can see from the field, from the circuit. This is Wheatstone bridge. This is Wheatstone bridge. You can see there we have, and this is an arrangement of four resistors P, Q, R, and S. P, Q, R are known. S is unknown resistance. So we have a source of EMF here. Then there is a key, or what we call a switch, and then there is a galvanometer which is introduced between point B and D. So this is the circuit, and this circuit is known as Wheatstone bridge. This circuit was given by a physicist Wheat. That is why it is Wheatstone was his name. So that's why it's known as Wheatstone bridge. So what is Wheatstone bridge? It is nothing but an arrangement of four resistances in which three are given, and the fourth one can be determined in terms of the three known resistances. Now two of the resistances P and Q are fixed. For example, P is 10 ohm, Q is 12 ohm. These two are fixed. Resistance S is varied. Resistance S is varied until the galvanometer shows no deflection. That is, the current in BD is zero. The current through the galvanometer is zero. Till then, we have to vary the resistance. For example, we will introduce a resistance of 5 ohm, then 10 ohm, then 15 ohm, then 20 ohm, until this galvanometer shows zero deflection. Again, I repeat, resistances P and Q are fixed. For example, P is equal to 10 ohm, Q is equal to 12 ohm. Now S is varied. We first introduce, we don't know what is this resistance S. It is varied. We use 10 ohm, 12 ohm, 13 ohm, 14 ohm till this galvanometer shows zero deflection. When the galvanometer shows zero deflection, we say that the bridge is balanced. That time the bridge is said to be balanced, and the resistance P, Q, R, and S are related as P by Q is equal to R by S. This implies R is equal to P S by Q. Now we know P because it is fixed. We know Q, it is also fixed. We know S because S is the resistance at which this bridge became balanced. So we can determine, using this relation, we can determine the resistance. Now we will prove this relation. Now look at this. When a potential difference V is applied across the bridge, a current I flows in the bridge. The current I divides itself at A. At point A, it divides itself into I1 and I2, which again combine at C to form I again by conservation of charge, because charge can neither be created nor destroyed. So the current which divides itself at A must be equal to the current which joins at C. Now here we have again three loops rather, two smaller loops, that is A, B and D, B, D and C. Then if we use a bigger loop, that is A, B, C and D. So apply Kirchhoff's second law, that is loop law, to the loop A, B, D and B, D, C, the two smaller loops. In loop first we get I1P plus IG, G minus I2R is equal to 0, because in this loop we do not have any source of EMF. In loop ABD, you can see yourself in loop ABD. Here we do not have any source of EMF. There is no EMF in this source. So that EMF is equal to 0. So applying this, that is why otherwise I1P plus IgG minus I2R should have been equal to EMF. But EMF here it is 0. There is no source of EMF in loop ABC. Similarly, I1Q minus I2S minus IgG is equal to 0 because E is equal to 0 in loop ADC also. ADC, it is rather BDC. It is BDC in blue BDC. Here it is not ADC, it is BDC. Now at balancer point. At balance point Ig is equal to 0, as I already told you, when the current through the galvanometer is 0, the bridge is said to be balanced. So at that time Ig will be equal to 0. This implies equation A becomes I1P minus I2R is equal to 0. This implies I1P is equal to I2R. Similarly, when Ig is equal to 0, equation B becomes I2Q minus I2S is equal to 0. This implies I2Q is equal to I2S. Now, dividing equation C by equation D, we get I1P divided by I1Q is equal to I2R divided by I2S. So I1 and I1 will cancel, I2 and I2 will also cancel. We get P by Q is equal to R by S. This implies R is equal to PS by Q. Hence proved. This is the relation for Wheatstone bridge. Now another application of this Wheatstone bridge or Kirchhoff's law is slide wire bridge. It is also known as a meter bridge. Slide wire bridge. It is also known as a meter bridge. What we do, here we have a jockey and we slide it over a wire. That is why it is called a slide wire bridge. We slide something over a wire. That what we slide over a wire is jockey. So that is why this is also known as a slide wire bridge. Now why it is called a meter bridge? Because the length of that wire over which we slide the jockey is 1 meter. That is why it is known as a meter bridge. So this wire is made up of manganese and its length is 1 meter and its cross section is uniform. It is stretched between the copper strips. We have two copper strips as you can see from the figure. So this wire is stretched between two copper strips on a horizontal wooden board. I mean, you can see it in the laboratory. If you go to the laboratory, you can see this beautiful bridge there. So a meter scale is also fixed on the wooden board parallel to the length of the wire. There is another copper strip fitted on the wooden board in order to provide two gaps between the strips. Across one gap, a resistance box R and in another gap, the unknown resistance S are connected. A jockey B can be slided on the bridge wire. One terminal of the sensitive galvanometer G is connected to a jockey B and another to terminal D. The positive pole of the battery E is connected to terminal A and the negative pole of the battery to terminal C through one-way key. The circuit is now exactly the same as that of the Wheatstone bridge as shown in figure. Now close key K and adjust the known resistance box for a suitable resistance R. Adjust the position of jockey on the wire C and B. Wire on pressing galvanometer shows no deflection. That is the current through the galvanometer is 0. Now note that length. So suppose that length AB is equal to L of the wire. Also note the length BC. That as the total length is equal to 100 centimeter. So the length BC will be 100 minus L. Now as the bridge is balanced, therefore according to Wheatstone bridge principle, P by Q is equal to R by S. Here P is equal to L R. Here P is equal to L R by R is the resistance per centimeter. So R into L will be the total resistance of the wire of length L. Q is equal to 100 minus L into R, where R is resistance per meter, per centimeter. So the remaining resistance Q will be equal to 100 minus L into R. This implies LR by 100 minus L R is equal to R by S, or S is equal to 100 minus L divided by L into R. Knowing L, that is the length at which this jockey, at which the ground will show zero deflection, that is L. And R1 we know, S we know, R1, R and S can be determined. Note the balance point is obtained in the middle of the slide wire bridge if the known resistance R is nearly equal to the unknown resistance S. If these two resistances are equal, then this balance point, suppose it is a 100 centimeter wire, the balance point will be at 50 centimeter. Okay, thank you. See you again.